What we have here is a conductor carrying a current perpendicular to a magnetic field. The magnetic field here is into the screen. Current is going left to right. We know from our studies so far that that conductor will experience a force that is both perpendicular to the magnetic field and the direction of the current. If you apply the left-hand rule here, it tells you that the force will be acting upwards. And we know that that force will be given by F equals B I L. B is the magnetic flux density, I is the current, and L is the length of the conductor that is in the magnetic field. However, we also know that the current flowing in that conductor will be the charge divided by time. So we can replace current in that formula I with the charge that's flowed through that conductor divided by the time that it's taken to flow, T. But of course, L over T, the distance travelled by the charge passing through the conductor divided by the time it's taken to travel through that distance, will be the speed of the charged particles passing through the conductor. So we can write F equals B Q V. In other words, it isn't just current carrying conductors that will experience a force. The charged particles, of course, that constitute that current must be experiencing a force. So if we've got any charged particle, charge Q, is moving perpendicular to a magnetic flux density B, at speed V, it will experience a force given by BQV. Now we can demonstrate that using the Teltron tube that we have set up here. So basically you can see the tube in the middle. It's basically an evacuated tube, there's a vacuum in there, and at one end, the right hand end, as you look at it, there is a metal filament. Now that filament is connected to a low voltage power supply that's just to the right of the Teltron tube, and we've set that low voltage supply to about 6 volts. And that's causing the filament to get warm, and thermionic emission then will take place. Electrons will be released from that filament. You will see 2 Helmholtz coils that are situated either side of the tube, and they are connected to a low voltage power supply on the left. And the Helmholtz coils here have been arranged so that the magnetic field will be coming out of the screen towards us. Now on the right we've got a high voltage power supply that we're going to set to several thousand volts. The high voltage is connected to the Teltron tube in such a way as to accelerate the negative electrons through the tube. So we've turned on the filament power supply, we've turned on the high voltage power supply, we haven't yet turned on the power to the Helmholtz coils, so we've no magnetic field there yet. What we should see is we've got a beam of electrons actually passing straight through the tube. Now you can see that here as we dim the lights. You can see that here, it's the blue line going across the middle of the plate. Okay, so we've got a nice straight line of electrons there going from right to left across that metal plate. Now remember, electrons are negatively charged. The direction of a current is the direction in which the positive charges would move. So electrons moving to the left, negative charges moving to the left, is equivalent to positive charges moving to the right. So as we have an electron beam moving right to left, that constitutes a current going left to right. So the current is going left to right. The field, remember, is coming out towards us, or will be out towards us when we turn on the power to the Helmholtz coils. Now, if you use the left-hand rule, what you'll find, you just put your second finger along the direction of the current, left to right, your first finger out towards you, your thumb will be pointing downwards. So what will happen is when we turn on the power to the Helmholtz coils and initiate a magnetic field here out of the screen, what will happen is those charged particles, the electrons, will experience a force which is downwards. And we should see a deflection of the beam then, which will be downwards. So here we go, turn on the power to the Helmholtz coils to produce a magnetic field. And if we start just to increase the voltage, you can now see that there is a deflection downwards. There we are, deflected the beam downwards. If we turn up the voltage, you can see it deflects downwards through a larger angle. An even larger voltage, even larger angle. The Teletron tube should be evacuated. There should be a vacuum in there. But the fact that we seem to have electrons deflected through different angles at the same strength of field suggests to me that maybe there's some air in our Teletron tube that's got in over the years, and the electrons are colliding with that, and so we end up with electrons travelling at different speeds. And as we shall see in a moment, if electrons are travelling at different speeds, they will be deflected by different amounts in the magnetic field. So the situation we had in the video was a magnetic field directed out of the screen. A situation we can show here, the dots indicate magnetic flux lines that are directed straight out towards us, out of the screen. And what we had was a negatively charged particle, minus Q, which was moving right to left. So there, its velocity v. Now remember, negatively, if it was a positively charged particle moving to the left, that would constitute a current moving to the left. But if it's a negatively charged particle, then the conventional current is taken to be to the right. And that means here that the force, using the left-hand rule, the force acting on this charged particle is directed downwards. The result of that, well, so what we find now is that the particle follows a curved path. It's forced downwards by the magnetic force and eventually arrive at a position here. If we think again about the direction of travel and the direction of the force, the direction of travel at that instant is along there. But if we use the left-hand rule, again, second finger, current is in the opposite direction to which the electron is moving. First finger out of the board. What we now find is that the force is in that direction. In other words, the force and velocity here are always going to be at right angles. And what we have here then is the conditions for the circular motion. Okay, remember basically here in circular motion, the resultant force is always perpendicular, always towards the center of the circular path. In this case, the magnetic force here is providing a force that's acting perpendicular always to the direction of travel of this particle. So two implications of that. First of all is that the magnetic force is not going to do any work, because if you remember the work done on an object, on a particle, is the force applied to it multiplied by the distance moved in the direction of the force. Well, look here, the velocity and the magnetic force, the velocity of the particle and the magnetic force are always at right angles. And what that means is it's never moving in the direction. The charged particle is never moving in the direction of the magnetic force. So because there's no distance moved in the direction of the force, there's no work done. So basically here, no work is done by the magnetic force. The magnetic force won't change the kinetic energy of the particle. It won't give it energy, it won't take energy away from it, it won't do work on it. And so the kinetic energy, the speed of the charged particle when moving perpendicular to a magnetic field, will be constant. The second implication then, although it's not doing work, what it is doing is it's changing its direction here. So the BQV force is actually providing the resultant force needed for circular motion. Now we know that centripetal force is given by mv squared over r. What we can do is cancel a v here on either side. We can say BQ is mv over r, and therefore the radius of the path is mv over bq. So let's say we had increased the speed of the particles by, let's say, increasing the accelerating voltage. The electrons travel faster, v is larger. What that means is we will increase the radius of the path as they move through the magnetic field. In other words, r is proportional to v. Doubling the speed of the particles will double their radius. If we increase the strength of the magnetic field, increase the magnetic flux density, B, that will reduce the radius of the curved path, the radius of the circular path, and so they'll follow a tighter path there. The radius will be reduced with a stronger field. If we continue on then the path of this particle, if it spends long enough in the field, what it will actually do, if I can draw it out, it'll actually trace out a circular path until it leaves the magnetic field. So charged particles follow circular paths in magnetic fields. As we said earlier, the BQV force here is providing the centripetal force for circular motion. And so R mv over BQ. Provided the mass and charge are constants, then the radius of the path is proportional to the speed of the particle and inversely proportional to the strength of the field. Now, what we can do is contrast that with the movement of charged particles through uniform electric fields. So, if I've got an electron, and let's say, again, it's moving right to left, and this time we've got an electric field. Now, in this particular case, the direction of the electric field is upwards, but of course here the direction of an electric field is the direction of the force on a positive charge. Here we have a negatively charged particle, so it's going to experience a force which is downwards. So here we can indicate the force on that electron initially is going to be downwards, which means to begin with the path of the electron is going to be similar. And it will follow a path like that. But important difference here, although it's following a curved path, here we've got a parabolic path. And here we had a circular path for the motion of the electron in the magnetic field. What is the difference? Well, as the electron starts to move and acquire a downward component to its velocity here, the force, the electric force on the electron, remains downwards. The direction of the electric force doesn't change. Whereas here the direction of the magnetic force changes, so it's always perpendicular to the direction of travel. Here the force is always in the same direction. The electric force is always here, well, for a negatively charged particle, in the opposite direction to the electric field. And so what happens in this case of an electric field, the electron just gets the horizontal component of its velocity remains the same, but the vertical component of its velocity increases, gets larger and larger and larger. And so what happens is the direction gets closer and closer to the vertical. And that is called a parabolic path. So it's never going to curve round on itself like this is done here in the magnetic field. Okay, so we have an example question here on this topic. Just take a moment here to look at the question. We've got a region of uniform magnetic field there shown by the black box where the flux density is 0.255 Tesla. We have moving into that field an ion which has got a charge of plus 1.6 times 10 to the minus 19 coulombs, and it tells us in the question also the mass of that ion, 3.82 times 10 to the minus 26 kilograms. And we can see there basically it moves around while it's in the field in a circular path as we would expect, and the diameter of that path there is 28.4 centimeters. We're asked first of all for the direction of the field. Now how can I do that? Well, straight away what I can see here is that I know as it moves in a circular path there must be a force acting perpendicular to the direction of travel, centripetal force. So as it enters here this field, as the charged particle enters the field here, at this point we know there's going to be a force acting perpendicular. The magnetic force there is providing the centripetal force later on. The magnetic force would be in this direction here later on. It could be in that direction there, always towards the center of the circular path if the object is performing circular motion. So we can use the left-hand rule at any of these points to work out the direction of the field. Let's see if we use this point here. It's a positively charged particle. Remember the direction of the current is the same direction as the positive charge is moving in. So second finger should be pointing left to right at this position here. We know the force is downwards, so the thumb has to point downwards. If you move your hand around, second finger has to point to the right, thumb has to point downwards, and if you have your hand pointing in those directions, you should find that your first finger now is pointing out of the screen towards you. So what is the direction of the field? Well, our answer there, part A, simply be out of the screen, out of the page if you're looking at it on an exam paper or something. Okay, so that's just using Fleming's left-hand rule. What about the speed of the ion? Well, we know here that in the magnetic field it is experiencing a force, and the magnitude of that force is given by BQV. Okay, the magnetic field, the direction of travel, both at right angles to one another, which means then we'll have the force will be BQ given by BQV, and that is providing the resultant force required for circular motion, which we know is also given by mv squared over r. What we can do is we can cancel that v with that one, and what we have then, if we rearrange that, v will equal bqr over m, and so we have the numbers to put that into that. So v here, the magnetic flux density, we were told that here is 0.255 Tesla. Charge on the ion, 1.6 times 10 to the minus 19 coulombs. Now don't forget, r is the radius of the circular path here, circular motion. Well, the diameter of the path is 28.4, so the radius is going to be 14.2. Don't forget to change it to meters. So there we've got the radius in, and we must divide that then by the mass of the particle, and we can work that out. And we get a value for the speed of the particle as 1.52 times 10 to the 5 meters per second. Quoted that to 3 significant figures to match the data given in the question. So there we are, simple as that. BQV, force, for any charged particle moving perpendicular to a magnetic field. And usually that will mean that the particle will follow a circular path in the magnetic field.